Thank you very much. And thank you for the introduction, and thank you also for the invitation. It's a pleasure for me to get to talk to you. It's an audience that I have not had the chance to talk to before, so I'm looking forward to it. All right, so the title here I think is a little bit tedious, but I'm going to talk about most of the words that I have here. We're going to talk about high-performance simulations of turbulent liquid atomization, so the process by which a liquid breaks up into droplets. We're going to mention a little bit of, we're going to say something about scalability. We're going to talk about conservation. We're going to show that we have converging methods. But ultimately, what I'm hoping to do here is to give you an idea of how we're trying to approach the issue that consists of solving discontinuous PDEs. The fact that we have different material properties in the liquid and in the gas means that we have equations that have discontinuities, and we're trying to deal with that efficiently. And so I'll show you how we do that. Whether it's the best or not remains to be decided. We're actively working on trying to figure this out. But it's certainly one way of doing that. All right, so let me start by, I should be able to remove, there we go. This top left corner is going to prove to be very useful. So I want to start by talking very briefly about some of my students. So I'm going to show you work that's been performed by a couple of my PhD students, Mark Oakes, who's pretty much done at this point, and Jeremy McCaslin. I'm going to show some work done by one of my postdocs, Peter Brady, who just started working at Los Alamos. The funding for this work comes from a couple of different sources. The more applied part of it is mostly funded by NSF. I'm sorry, the less applied part of it is mostly funded by NSF. The more applied part of it is funded mostly by companies who have to deal with multiphase flow problems, and they can't simply use computational software like Fluence in order to solve the problems. I'm going to show you some fairly large simulations, and so for that we happily make use of federal resources. A couple of different places have been very good to us in the past, in particular Oak Ridge National Lab and Lawrence Livermore National Lab provided us with access to some of the largest supercomputers in the world. In this list, I think Sequoia is now maybe number 2, Titan might be number 3, it might have slipped to number 4 or 5 in the world. Exceed is the NSF program, where I don't know exactly what Stampede is, but Kraken a year or 2 ago was number 1. It's now number something 7. Yeah, those are pretty cool names. I agree. So I'll show you simulations done on Sierra, simulations done on Kraken, and simulations done on Titan. All awesome names. All right, so that's the acknowledgments. Let me start by just giving you a little bit of a layout. I have really mostly 3 parts to my talk. I want to motivate why we even care about liquids breaking up, so I want to spend a little bit of time on that, explain to you a little bit about the challenges, and hopefully convince you that it's an interesting problem and that it's a very impactful problem for society. Then we'll talk about numerics. We'll talk about numerics, and I'll go through some aspects of the methods we use, and I'll try to walk you through probably what ultimately is the most basic part of it, but hopefully you'll find this as interesting as me and my students. We're pretty excited when we think about those simple ideas for transporting discontinuous quantities. We'll say very little, but we'll say something about consistency. This thing just died on me, I think. Consistency and scalability, but I'll limit myself to a couple of slides on that. And then the third part will be just more, I would say, eye candy than anything else. I'll show you some simulations, and I'll show you a little bit of validation. We'll go to a very big problem of liquid jet atomizing in the crossflow, and then we'll go to a problem that's not quite as big, but maybe a bit more exciting. It's more an emerging problem that couples Maxwell's equations with Navier-Stokes, where we're looking at using electrostatic charges to help us break up liquids. All right? So before I start, I'll just give you a one-slide overview of some of the stuff we do in my lab. So we're focusing on computational thermofluid problems. Mostly, we're looking at multi-physics and multi-scale problems. The fact that we're looking at turbulence kind of means that we're systematically looking at multi-scale problems. And we try to exploit large-scale, what we call leadership class computing facilities that are available in the US. We try to use those resources to shed some light on those problems. There's three categories of activities that we do to various degrees. We are interested in the fundamental physics of multiphase reacting turbulent flows. Less reacting, more multiphase nowadays. So we're interested in looking, for example, at how would one describe the breakup of liquid from a statistical perspective. That's something for which someone like Komrogorov has done quite a bit of work, but there's still a pretty clear need for better fragmentation theory applied to liquid gas flows. We're doing quite a bit of numerical method development. So we're looking at liquid gas flow, tracking interfaces, solving equations for evaporating liquids. We're interested in tracking particles, large numbers of colliding particles, doing that efficiently. We're developing Euler methods to deal with particle-laden flows. So that's quite a bit of what we do is focused on methods. And then when we have both the methods and better understanding of the physics, we tend to start looking at modeling questions. How can we use a coarser mesh and try to model what's happening at the smaller scales? How can we bring back some of what we've learned about the physics of the flow to Reynolds-Savage, Navier-Stokes type of level that the industry could use in the form of a simple parameterized model. And so we'll talk really here only about those types of flow where liquids break up. An entire other part of what we do involves turbulent transport of particles. Here, this is a bed of sand in a pipeline being lifted out by a turbulent liquid flow. Here, we're looking at combustion instabilities. This is a spray flame, but we won't talk about this. All right, so let us start with a little bit of motivation, why we care about this. So I thought I'll use the source of information that hopefully everyone will be comfortable with, which is Urie's annual energy outlook. I'm showing here the one from last year, but I'm actually using old data from 2010, I think, that I kind of forgot to update, so sorry about that. And I'm also, I think one graph is from the early release of the 2014 report that will come out in a couple of months. But I want to just get a very few simple ideas across, and nothing should be really new to you. One very simple statement here, what this graph shows is that our energy consumption will increase. Those are projections 30 years down the road. Everything suggests that we will use more energy. That's not a big surprise. And that petroleum and liquid fuels in general will remain the biggest way, the most frequent way that we're consuming energy. All right, so liquids matter quite a bit. And they also matter because if you look at CO2 emissions, they still represent, in particular due to transportation, so here the petroleum is this brown color. Transportation represents a very significant fraction of CO2 emissions, and that's entirely petroleum, or almost entirely petroleum. And the industry, there's also quite a bit of liquid fuels being burned, and that's also contributing quite a bit to CO2 emissions. So really, CO2 emissions are also mostly due to petroleum, to burning petroleum, all right? The last point I'll make here is that if you look at electricity generation, and there's different ways you can look at that, but if you're interested in renewable energies, it turns out that most of that is being driven by the federal government towards liquid fuels produced from biomass. So we're definitely heading towards producing liquid fuels based on renewable material, and that's in order to displace petroleum-based fuels for transportation. So the three key ideas here is that we burn lots of fuels. Most of the main way we use energy is by burning fuel. By doing that, we have the most impact on the climate, and the fuels that we're burning are evolving. So year after year in the projections, 30, 40 years down the road, will be burning still lots of liquid fuels, but they'll be different. They'll have different material properties, they will atomize differently, they will burn differently. So if we want to impact energy consumption, reduce that, if we want to reduce pollutant emission, and if we want to be ready for the transition to biomass-based liquid fuels, we need to understand atomization. So that's an experimental picture of what's going on in a gas turbine engine combustion chamber. You're looking here at an N-heptane spray being injected here, and then you have a nice flame that's stabilized because of swirl, so you form a nice cone. You see this yellowish color here because this is a soothing flame. This image is from Bowman's group at Stanford, at 10 years old or so. But that illustrates pretty much what's going on in an aircraft gas turbine engine. But it also is representative of what's going on in stationary gas turbine engines. It's very much representative of what's going on also in car engines. So this is very much what we do when we burn fuels. We first have our liquid. We know that we need, for combustion to take place, to bring it into the gaseous phase. Combustion is a gaseous process. So we need to evaporate it. In order to evaporate it efficiently, we need to increase the surface area of that of contact between the liquid and the gas. We do that by replacing this liquid by a large number of drops. Therefore, we form a spray. All right. This process is, I would argue, fairly well understood. The turbulent combustion process, something that was, my almost next door neighbor, Steve Pope, is working heavily on. That's something that we understand reasonably well. We have very good tools for modeling that. There's been a lot of progress in this area. I actually started my PhD doing this type of simulations. This is not an experiment, but I started my PhD simulating that experiment. And I was using state-of-the-art turbulent combustion models. And everything was working great until I realized that I could really get very much any result I wanted by tweaking the way I was specifying my spray boundary condition. So I got less interested in turbulent combustion and more interested in turbulent atomization. I thought, this is something that we're going to need to figure out. And really at this point I would argue that this is the process that is the least understood in the global turbulent combustion phenomenon. So I would argue that we need to focus on that right now. And the reason is clear. The atomization process controls the drop size distribution, controls where the spray is going to be located, how big it's going to be, which in turn will control where the flame is going to sit, how efficiently it's going to convert, it's going to burn basically, and ultimately it will control how much fuel we consume and how much pollutants we produce. So if we want to consume less fuel, generate less pollution, we need to know how to improve the atomization process. So now here comes the tricky part. How do we do that? Well, we can do experiments, we can do theory, there's many things we could do. Why use simulations to look at that? Well, it turns out simulations, I would argue, are probably at this point the most effective way to approach that problem. We do have ever-growing computational resources available. This is I believe it's the latest top 500.org graph that shows the sum of all supercomputing resources in the world, the largest supercomputer in the world, and the number of 500 in the list. The power in terms of flops as a function of time. So you can see we're still sticking to a nice exponential growth here. So we have lots of resources available. So we can pretend to use those resources to attack the problem of turbulent atomization. I think it is at this point easier to do that through simulations than by doing experiments. The issue with experiments is that if you have an atomizing liquid, you're forming droplets everywhere around the atomization region. You can't take a picture, it's going to be obscured by the presence of the drops. You can't shoot a laser, it's going to be deflected by the presence of the drops. Doing measurements is incredibly complicated. So at this point, the most successful approach for doing experiments, quantitative experiments on sprays, is to, on the fundamental atomization process, is to shoot ultra-fast X-rays through your atomizing jet. That means moving your experimental apparatus to Argonne National Lab and using their $1 billion facility the advanced photonic source, you have to write a proposal, wait several years to get a week of time there. It's not easy. It's a nightmare to simply try to put a pressurized vessel. All those systems we're talking about, combustion chambers, they're all pressurized. How do you shoot this ultra-fast X-rays through a pressurized vessel? This is incredibly complicated and expensive. So experiments are difficult. Theory is limited. We know very well how one drop will detach from a dripping faucet. We have fantastic theory, the math works well. This is not the problem. The problem is a problem of scale. What happens if we now have a much bigger system with much higher velocity, much more inertia, and much larger range of scales? What's going to happen? What controls the fragmentation process? There's theories there, but there's no validated theory because we don't have data. Yes?
It's very clear. I do agree. Atomization is, I don't know if it's question. It's the breakup of the fluid. This is fragmentation, basically.
Yeah, this is fragmentation.
It's do the same thing.
Yeah, yeah. It's fragmentation. Yeah. So there are theories for fragmentation. The issue is that those theories usually make assumptions on the number of fragmentation events that take you to your final size. There's assumptions on the scale dependence of the fragmentation process. We don't know how this actually works on larger scale systems.
So, excuse me, you care about how turbulence takes some material surface of some 3D material volume?
Yes.
Okay.
We're looking at the catastrophic process of destroying a blob of liquid into a fine spray. Well, let me show you. So, why is it difficult even to do simulations? Well, it's difficult because effectively, as far as we're concerned, we're looking at that from a continuum standpoint. We want to solve the Navier-Stokes equations. Our liquid-gas interface is thin enough that it's effectively a discontinuity. So we want to solve a discontinuous problem. This problem is also quite difficult because we have very wide density variations from one side of the interface to the other. That means that inertia is going to be crazy. The amount of momentum might be the same on the liquid and on the gas side, but on one side it's going to be because we have a high velocity gas with low density, and the other side you're going to have a very slow liquid with very high density. You can imagine that numerically, if you want to interpolate between those widely varying quantities, you're going to have trouble. So we'll talk a bit about that. The reason why this guy up here is not sinking is because we also have a surface tension force. That's a singular force that exists only on that surface. So we need ways of modeling that. Not necessarily specifically that process of this guy running, but the effect of surface tension. And then I think the question about the catastrophic fragmentation due to turbulence, this guy is showing that really well to us, and this process here is also a nice way of illustrating that. The topology change of the interface is incredibly complicated.
Could you say a little more what's happening in the bottom?
Yeah, absolutely. So you have a balloon filled up with water, and then there's some sort of a pin here that hits it and breaks it up. So the first thing that happens is you have the water jetting out, and you can see that there's a nice electrohydrodynamic instability forming. It's just pretty, and then what you see is you have this mushroom shape that forms, and you end up inflating like a water balloon.
Yeah.
You have a sheet of liquid that's being inflated. This is what we call back breakup, and then what happens is this goes down to literally a few tens of angstroms size, and it just breaks. And when it breaks, it bursts into very small ligaments and very large number of droplets.
And then there's something that's sort of hovering above. Is that just a piece of the balloon?
This
right
thing
there,
here,
that thing.
That's, I think, is the pin that breaks
That's the pin.
Yeah, I
Okay.
believe so.
It has bounced back off.
Yeah, I'm not. Most likely.
No.
All right. So that's, I guess, my my little motivational speech that I give to incoming students in my group. This is why we care about this. This is a difficult, exciting problem. Now let's try to figure out how to solve it. And so I'm gonna say a few things. First, I'll set the stage. We'll just write down the equations, and we'll start making a few assumptions. First, we'll say most of those dynamics can be handled using an assumption of incompressibility. Those are fairly low speed flows, regardless of the level of turbulence. They're still low speed. So we're going to assume that everything is compressible. We're not going to worry about phase change. We're going to simply deal with a liquid, a gas. Those are two immiscible materials separated by an interface, and we're going to be assuming that everything is incompressible. So that means that full velocity field is solenoidal. All right. That means that our continuity equation, conservation of mass here, rho is the density, is just a simple statement of material transport of the density. We're saying that the liquid-gas interface moves due to the velocity field. And then we can write Navier-Stokes in both phases, so that this is written in terms of momentum, rho u, we have the temporal change, this is convection, we have the effect of pressure, and then this is our viscous term, which looks in many ways like a viscosity coefficient times the Laplacian of the velocity. And then we can include gravity. So that's all fine. The issue is that, well, the correct picture is that those equations are valid on both sides of the interface, but at the interface, which I've called gamma here, the metal properties are discontinuous. That means that we have a jump in density. So we go from rho liquid to rho gas. We have a jump in viscosity. We go from mu liquid to mu gas. The velocity field itself, if we assume that we have a viscous flow, which is a reasonable thing to do, and if we don't have any phase change, the velocity field itself is going to be continuous. The derivatives of the velocity fields are not going to be continuous, but the velocity field itself is continuous. So there's no jump in velocity. There is a jump in pressure due to the fact that we have a surface tension force, so that's how we're going to model our surface tension force. Let's not worry too much about this term. The sigma here is a surface tension coefficient. We're going to assume that if we multiply that with the local curvature of our interface, it's a good model for the normal pressure force of the interface. So the sigma here is a surface tension coefficient. It's a property of the interface. We're going to assume that it is constant. And kappa is the interface curvature that we can access, for example, by taking the divergence of the interface normal vector.
So you mentioned that there's no actual change of phase, but eventually you will end up having a change, no?
Right, so if we're interested in the combustion process, yes, we will evaporate all this. So there's an inherent assumption of difference in time scales here. What I'm saying is the process by which we atomize our fuel is much faster. So we'll first have a coherent liquid, we'll break it up into a spray, and then this spray will move around in the domain and evaporate on a slower time scale. That's the assumption we're making. It's not necessarily a terribly bad assumption, but most experimental data at this point for atomization is available in isothermal systems where there's very little evaporation. So it's not an unreasonable starting point.
So then the total volume of the fluid you have in the beginning is the first is conserved?
It is conserved, yes.
Whereas if you had these additional factors you mentioned, then you have all the...
Yes. Yes, and the conservation of this liquid volume is actually a critical issue.
I don't envy what you have already.
But we're going to talk about that. So let me start by making a wish list for numerics that we'd want to use. So there's a number of things that would be ideally available in order to simulate turbulent atomization. First, we need a way of tracking our liquid-gas interface. We don't know a priori where it is. We need to solve for that. We need a way of dealing with the fact that the density is so different between the two phases. And so we'll talk briefly about that. Most atomization devices that exist in engineering systems are extremely complicated. The idea is always to induce very strong vortices in order to break up the liquid. So usually the geometry of those systems is complex, so we need ways of efficiently handling complex geometries. We're not going to really say anything about that. We need to be able to simulate turbulence. Almost all those flows involving atomization are turbulent. We're not going to say much on that either. And then finally, the approach that we're proposing to use is to brute force really this problem. We're saying we have leadership class computing facilities, and we have a problem that's of high societal relevance. We need to know how to better design injectors. If you're all driving a car, if we can improve by a few percent the fuel consumption and reduce the pollutant emission for all the cars out there, we would have a huge impact. It is worthwhile to bring to bear this huge computational resources to try to brute force to get a solution to that problem.
Is the topology of the interfaces an issue for you?
It is.
Because, I mean, they certainly change dramatically.
Yes. So there's going to be multiple issues. There's certain topologies, in particular sheets, that can remain stable for very long times with very, very small thicknesses. That's a struggle for us. Ligaments, tubes, are inherently unstable. If you have their diameter oscillate a little bit, they'll break up really rapidly. As long as we capture the onset of this instability, what we call Rayleigh plateau instability, we'll capture the breakup really well. So we're not worried about ligaments, but sheets are incredibly problematic. And also the additional requirement is we need methods that allow us to deal with very, very frequent topology changes, which does put a restriction on the methods.
But I mean, even the theory of how a single drop pinches on a string of fluid, it involves a very complicated amount of geometry.
Right. So so there's multiple problems. The very details of the final stage of the breakup are not controlled by Navier-Stokes. So this is not even approachable by this approach. But it also doesn't really matter much. We're talking about picoliters of fluid that might end up in the drop or on the other side of the drop. So this is a very minute modeling issue that can be important in certain situations, but I would argue in most instances might not be all that relevant.
But isn't one of the main things that you're interested in the size of the drops?
Right, but capturing the Rayleigh plateau instability that leads to the breakup of that drop will lead to a very robust prediction of the drop size. So as long as you get the initial linear growth, I should say exponential growth of that instability, you'll get the right drop volume within a very, very small area. The very details of the pinching off process is much, much more complicated, and it happens at a molecular level. This we won't get, but this matters very little. All right, so there's many methods out there. I'll just give you a very, very brief overview of some of the approaches that exist. Since we're looking at discontinuous systems of equations, why not simply create a grid on both sides? So a grid in a liquid, a grid in a gas. That's a good idea, but this comes back to your question, how do we deal with very complicated topology changes? It's impossible. You can't constantly remesh and reorganize your discretization of the domain to accommodate the fact that you just pinched off a little drop. So this is not really applicable. The same way you could use a simple structured grid to represent a computational domain and then introduce a secondary mesh that could be a surface mesh in 3D or a line mesh in 2D to represent the location of the interface. That is also very much problematic if you need to deal with very frequent topology changes. You need to know how to break this up. So methods that automatically handle topology changes, for better or for worse, there's really two of them, the level set method and volume of fluid method. Volume of fluid method, the idea is to simply track the fraction of the cell that is in the liquid. So the cell that's fully liquid would have a value of 1, cell that's fully gas has a volume of fluid value of 0, and then mixed cells would have an interface, liquid-gas interface in them, and we can solve an equation for how this field evolves. This is very good for conservation. It's not necessarily a very easy method to use, and we'll talk about that quite a bit. Level set is actually what I spent most of my time working with, even though we will talk here about volume of fluid method. But level sets, it's a very well-known mathematical or applied math trick where you have an interface that you want to follow. You're going to replace it by an auxiliary function that we call a level set function, defined such that one of the isosurfaces of one of the isocontours of that auxiliary function coincides with the interface. Now you can define that level set function to be as smooth as you want, and you can transport it easily. There's lots of additional complexities associated with that, but that's the main issue with a method like a level set method is that inherently this function that you're using is a pure mathematical construct. It's not a function that has any physical meaning, and therefore introducing conservation properties in that method is extremely complicated. It's going to be very difficult for us to conserve the amount of liquid volume in a simulation using that method. I actually spent quite a bit of time during my PhD and a little bit after that modifying classical level set methods to reintroduce conservation properties. And so to look at a complex atomization problem, a standard level set method might actually lose 100% of the mass. All your errors might show up in the form of spurious motion of the surface, such that you end up losing all your small drops. Every time you have a drop pinching off due to mesh resolution limitations, it might just simply kind of diffuse away because you have because you have diffusion errors in your transport scheme. So you might end up losing all your liquid as it undergoes breakdown. So that's not acceptable. So I worked on methods that brought down this 100% error to 2-3%. And I was really proud of myself until people in the industry came back and said, well, that's terrible, 3%. If you mess up your amount of fuel by 3%, you might mess up the temperature in your combustion chamber by 5 Kelvin. And 5 Kelvin might play a huge role when you try to predict NOx. NOx production is proportional, is an exponential function of the temperature. So you might actually be a factor of 1 away in your NOx production. And it turns out most of the current engine redesigns are done because of more stricter legislation on NOx emissions. So 3% is not acceptable. So we went back, and recently in the past couple of years we've started moving back to a method that's more fundamentally built around the idea of conservation, and that's volume of fluid. So that's what I'm going to talk about here. So imagine, take a very pretty atomization picture like this one. It's probably one of the prettiest out there. A combination of a Kelvin-almost instability, and the azimuthal direction, you can't really see it, but there's a Rayleigh-Taylor instability. And then you pull out ligaments because of the high-speed gas stream around, and then those undergo Rayleigh-Plateau instability. So there's an entire nice little theory that describes the interplay between the three piggybacking instabilities. So let's take this pretty picture and make it not quite as pretty. We're going to introduce a liquid distribution function, let's call it chi. We're going to say it is equal to 1 if we're in the liquid, 0 if we're in the gas. It's not particularly difficult, it's just a heaviside function. And then we're going to consider a computational cell, and in that cell, we're going to introduce a volume of fluid in the form of the liquid volume fraction. We're going to call that alpha. And I'm calling it here the zero-order moment of chi on this volume, but it's just basically the 1 over the volume of that cell times the integral of chi over that volume. Right? So that's the amount of liquid volume in that cell divided by the volume of the cell. If it's 1, it's entirely liquid. If it's 0, it's entirely gas. So then imagine we have a field like that at time n. Those alpha fields are now mesh. That cell is kind of a trivial thing. This is 1. Therefore, the cell is entirely liquid. We know that there's no interface in this cell. You might have here a cell that's alpha is equal to 0. It would be entirely gas. There's no interface here. But how can we figure out where the liquid-gas interface is located in those mixed cells? So this problem has been solved, or at least an answer has been provided. So I will just mention it briefly, and I'll take the opportunity also to ask you a question. But if you just use that method, this is the so-called piecewise linear interface calculation, PLIC. It's been around for 30 years or so. Then this is the assumption you're doing. You're saying you know what alpha is in that cell, and you assume that in some way you've figured out what the normal orientation of the interface was in that cell. And that's something that, it's an entire other kind of worms. We won't discuss that, but using neighbors, information, the volume fraction from neighbors, you can estimate what the orientation of the interface should be. From that information, the problem of PLIC is to try to figure out where to place a plane in that cell such that the plane is normal to that normal vector n, and you have exactly alpha times the volume of that cell under that plane. All right? That's the problem that we're trying to solve. It's a solved problem. It's not the most elegant problem out there, but you can compute a few different quantities, you can use symmetries in the problem, and you end up having to solve a cubic equation. You can solve it. It's a problem that's solved anyway. So what we're doing here with SPLIC is we're reconstructing our liquid distribution function chi from the zero-order moment. All right? One of the things that, at this point, the entire community looking at multiphase flows is stuck on this. This is the best that we can do. We don't know how to do a more accurate reconstruction of the liquid distribution within the cell. And that's something that if you have ideas, I'd be really happy to discuss with you about that. How do we move away from that? How, for example, if I were to give you not only the volume fraction, but also the liquid barycenter, the center of mass of liquid in the cell, how would you estimate more accurately where the liquid is supposed to be in that cell? That's a difficult problem. it's probably a solvable problem, but it's also a kind of tedious problem because of the geometry of that cell.
Is this strategy constraining the cells that are small compared to the droplet size? Do you have to use cells that are small compared to the droplet size?
Yes. Yes. Yeah, the fact that we have a planar approximation of the interface means that we have inherently a second order error, so the smaller the cell, the better. But anyway, now we have an algorithm that takes us from alpha to an estimation of where the interface is located, and that's a second order process. Now we need to transport that field. How do we get at the new time and +1 information of where the interface is located? Well, so we can write fluxes at the faces, standard control volume approach. Those F's here are the amount of liquid that within the time step, the amount of liquid volume that will enter or leave the cell within the time step. If you divide that by the cell volume, you end up with an update for your alpha quantity in the cell. So that's reasonable to write. It's pretty standard. The question is, how do you build those fluxes? If you use standard finite difference or finite volume discretization, we kind of know what the problem is. We're looking here at a field that's very sharp. The alpha field is the zeroth order moment of a discontinuous quantity. If we use low-order accurate schemes, we can remain bounded between 0 and 1, but we'll have diffusive errors, and we'll end up having many, many cells that have successive values of alpha that are somewhere between 0 and 1. We lose the sharpness of our function. We can't really define anymore where the liquid gas interface is located. If you use high-order schemes, you can have much sharper solutions, but then you have Gibson phenomenon, and you're going to have to struggle with overshoots and undershoots. Your volume fraction will be less than 0. You'll have less than 0% liquid or more than 100% liquid in your cell, which is meaningless. So you have to resort to something different. So there's been a number of methods, yes.
What's high order for you? Like 3? 2?
This was 5,
Okay.
but the same thing is happening if you use a 7th order discontinuous Galerkin scheme. You can go as high as you want. It's still, if you want to be bounded formally with high order, you're going to have to use a limiter that will bring down the order of accuracy and we're going to produce diffusion.
But you think of 5 is pretty high. Some people say 2 or 3.
Yeah, no, this was, the top one was one, simple upwind transport. The last one was a 5th order winner.
Thank you.
All right, so now that means that we can't use standard schemes, and instead we're going to have to rely on more geometric considerations. We're going to have to use information about the geometry of our liquid gas interface in order to have non-diffusive transport. It is very important for us to have non-diffusive transport. There's a family of methods that have been around for a while, which essentially rely on semi-Lagrangian mapping of the cell faces in order to figure out how much geometrically should flux through each face. So if I take that face and I take it back in time in a Lagrangian fashion, I look at where it used to be if it were to have followed the flow, then I can figure out the swept volume of fluid, the volume of fluid that's swept by the face during the time step, and I know that everything within that swept volume will have to go through that phase within my time step. Now if I can compute the amount of liquid that I have in that swept volume, I directly know how much liquid should come in through the phase. This might sound like hand waving, but this is just very easy to obtain. You just have to, it's Reynolds transport theorem, or you probably prefer to think of it as as a Leibniz rule. You can very easily write that the change of the integral of the quantity of the control volume is due to the sum of the stuff that fluxes in and out, which can be written as the integral of the quantity at the old time over the positively swept volume in the domain by the phase and the negatively swept volume. So this is easy to show. Yes?
In the actual calculation, you're not able to actually track that curvature you're drawing in the strip tube?
Well, we'll talk about that in a second.
Okay.
So we're forming here a strip tube emitted from the face, and we want to know how much liquid we have in that. People have been doing that for almost 30 years. The first version of that was very simple. People were forming the strip tubes by simply taking, for x faces, the x velocity. They were pushing back in the horizontal direction the face and they were figuring out how much liquid they had here. And then they had to transport in Y and then in Z. So this was fundamentally a split scheme. So they had we had very large splitting errors for this. It was not a particularly good scheme, but that was the first version of that. And people started thinking, well, I could define for my phase a full two-dimensional velocity and bring my phase back in time along a multi-dimensional velocity direction and see what happens to it then. That's much better. You reduce the splitting errors quite a bit. What happens, though, is that your swept volumes from neighbors to neighbors can overlap. That means that if you have a little bit of liquid in this overlapping region, you're transporting it twice. It goes through that phase and that phase. That means you're not conservative, you're not going to be bounded. More recently, 2004, Lopez and al., they figured out how to do that. They started using vertex-based velocities in order to take their phase back in time. Then you guarantee that you're not going to have any overlap between the neighboring swept volumes on street tubes. They did that only in 2D, though, and this was a pretty tedious exercise already. In 3D, people started doing things like, for example, for each phase, they created a velocity for each edge center. That's still a second-order accurate estimate. You have a full three-dimensional velocity at the middle of the edge. That allows you to form a second-order accurate estimate of what the street tube should be. And also, you don't have overlap between neighbors. But in the diagonal direction, you can still have overlap between swept volumes. So it's still not conservative and still not a bounded method. So my grad student, Mark, last year started working on that and said, well, why not simply bite the bullet and do the full thing? Each vertex should have a full three-dimensional velocity, making sure that each vertex is shared between the faces and uses the same velocity guarantees that we'll never have any overlap between the street tubes. So in theory, we're all fine. So, yeah, perfect. Let's hope. This is discretely conservative, discretely bounded. It has additional properties, but it's also formally second-order accurate. So what's the challenge? Why people didn't start doing that before? Well, let's consider this configuration. That seems fine, but we have A, B, C, D. This is the volume that goes through that phase. You can already see that in the context of a general velocity field, you could also have A, B, C, D, a crossed polyhedron like this. It's a very acceptable solution. Part of the swept volume goes to the left, part goes to the right. That's something that will happen. We need to be able to deal with that. Now you take this in 3D, and this is the type of shapes you get. You'll have multiple subregions that will go from left to right, multiple regions that will go from right to left. And this intersection point doesn't lie, don't trust this projection, it doesn't lie on the face. It's going to be outside of the face. We're going to get pretty crazy geometry. So how do we deal with that? Well, it turns out, it took us a little while, but we realized that it's almost a trivial problem. If I split this guy into two simplices, in this case two triangles, A, B, C, and A, C, D, and I orient them such that their orientation is of the same sign as the fluxing direction, so those move in the phase, so in the control volume they're positive, and so they're both defined such that they're positive, they give me a reasonable second-order representation of that flux volume. And when I go to that complicated shape, if I stick to the same two simplices with the same order, A, B, C, and A, C, D, and A, C, D, using the right-hand rule, is still a positive quantity. It fluxes into my control volume. But A, B, C now, using the right-hand rule, is now a negative tet. It's flipped over itself. So even though I have this region here that's now covered, that really doesn't exist here, this thing should not be fluxed. I'm going to be fluxing it once negatively, once positively. It cancels out. We still have a very simple and very appropriate representation of the swept volume. And this works beautifully in 3D as well. So that's, in the end, what we do. We want to build this. Well, we create the velocities at the vertices. We take this back in time. We do an approximation in the form of a collection of simplices. We orient very simply our simplices. And then what we need to know is how much of each simplex is in the liquid. This is just an issue of intersecting a simplex with the plane that we reconstructed a few slides ago using what we call PLIC. That's a simple problem. It's a margin test problem. It's an easy thing. So there we go. We have a method now that's exactly conservative, exactly bounded, and it's also formally second-order accurate. There's nothing that we do that should violate that. So here we're playing with a drop that we put in a specified velocity field, and we can recover this perfect second-order convergence. All right. I want to say two quick things about numerics. One is, this is a very busy slide. I'll just say one thing. And actually, to do that, I'll go back here. We're just talking here about transporting the amount of liquid volume, but imagine now if I have any other discontinuous quantity I want to transport. Now I have separated the liquid fraction of my swept volume from the gas version of the gas part of my swept volume. If I want to compute the discontinuous momentum, I just need to have an approximation for velocity, and then I multiply it by my liquid density here and my gas density here. And now I have a discrete second-order handling of any type of discontinuity that's tied to the liquid-gas interface. If I want to solve an equation that exists only in the liquid, that's fine. I just rescale my flux by this volume fraction. I have to flux quantity here, but nothing here. So I can deal with discontinuous problems very easily in this frame. And so that's something that we need to do for momentum, and I'll give you one example and then I'll answer your question. If you don't do that, and take a pretty crazy test case like no viscosity, large density ratio, and you start letting a drop a billion times heavier than the gas around it move from left to right. If you don't have the discrete consistency of handling the discontinuities, everything blows up. It shouldn't be a surprise. All your errors, interpolation errors between density and velocity, will be amplified by a factor of a billion. You'll be generating crazy amounts of momentum. If you're consistent, this is still a difficult problem, but it shouldn't be a robustness problem. You're still formally second-order accurate. We have discrete conservation of momentum. There's no reason why anything should blow up. And yes, you have deformation. Yes, it's not perfect, but you get something that runs. Yes?
Yeah, so coming back to the question I made, you actually don't track the curvature like in a sub-grid
No,
fashion?
we could. So you have control on the number of TETs you use. We've done discretizations using, in 3D, 5, 6, 20, 24 TETs. You can account for some of the curvature of the streak tube. It becomes expensive very fast. We've never really found much interest in doing that. All right, I said I would talk briefly about scalability. It's an important issue. We're solving incompressible equations. We have to deal with the Poisson equation, which also involves discontinuous coefficients. I didn't talk about that. But so we have a careful part implementation of a black box multi-grid solver. Basically, we need to be aware of the issue of scalability. I'll just show you a couple of scalability plots here. I think the biggest one is down here. This is done on Kraken. This is a 1.2 billion cell simulation on almost 50,000 cores. This is linear scaling. And you can see that, yeah, we don't have perfect linear scaling, but we're about 75% of the way. That means that we waste about 25% of our time doing excessive communications or dealing with I/O jitter or things like this. But overall, we're fairly scalable, so we're capable of using those methods on very big systems. All right, now I just want to show you a little bit of, I'll basically show you two main applications. But the idea is we can use all this to look at a number of different flows that are relevant to a number of different energy systems. This is, for example, a pressure swirl atomizer. We're looking here at a liquid injection through inclined pipes that force the flow to swirl very strongly. And actually, with air kind of is brought back all the way to the back of the injector here. This is the type of system that's used for example, agricultural spraying, painting-related applications. There's many systems that use pressure swirl atomizers. Gas turbine engines typically use quite a bit more complicated systems. They have a pressure swirl atomizer, and then they combine a second co-flowing swirler that injects some additional amount of fuel so that you can have one or two injectors per injection head. And they also have in general an air blast type configuration, which means that you have also a co-flowing gas stream that's very fast, so that you can make sure that the sheet that you create due to the pressure swell atomizer is completely destroyed by the impacting gas stream. If you look at your car engine or a lawnmower engine, you're going to have a direct high pressure jet that comes out straight into the combustion chamber, and that corresponds more to this configuration of a straightforward turbulent liquid jet that breaks up if this thing ever wants to go. There we go. So the first case that I want to talk about, and I'll show you a little bit of data on this, is a liquid jet and cross-flow atomization problem. This is an 8 billion cell simulation done on 12,000 cores, and we're resolving down to approximately the smallest drop size observed. So this doesn't necessarily, we're not necessarily capturing absolutely all scales, where the smallest drops are resolved only on a couple of cells in terms of the diameter. But we also expect that there's very little happening on that scale. But there's no mass loss here. We're capturing, we're not losing any mass. The configuration is we have liquid being injected at fairly high speed into a turbulent crossflow. And so the jet entirely bends over, and then we end up seeing breakup. This application is typically what's the way we inject fuel in scramjets, for example. But then this would be supersonic, and we would have a shock wave in front of it. At lower speeds like that, it's more representative of what we call augmenters. So, what Hollywood would call post-combustion. So, re-injecting fuel in the exhaust stream of a gas turbine engine to get additional propulsion. So that's a configuration. I think I have a quick movie of that. So that's how this looks. You can see that the column bands, we have very large scale instabilities developing. We're forming drops. These drops break fairly rapidly due to shearing into droplets. There's a couple of questions that are of interest. One of them is, what is the impact of the shape of the liquid injector? So here we're comparing a round edge injector for the liquid stream to a sharp edge injector that's expected to lead to more turbulence. And so, we could see that we had more turbulence and more breakup when using the sharp injector. But really, ultimately, our interest was to try to do a little bit of validation. And so we did have experimental data for that coming from Georgia Tech. One of the things that they measured was the trajectory of the jet for those two injectors. And that's those red lines. And we're comparing that with our simulations. You can see that in the case of the turbulent flow, the jet is quite a bit straighter, and we do seem to follow very, very nicely the experimental penetration result. In the case of the round injector, that's more of a laminar injector, we do not follow quite as nicely what's going on here, and we believe that this is because we're mischaracterizing the turbulence in the cross stream. We have very little data on this, and so our representation of it upstream of the jet is very naive. So we believe that we could probably get better results here. And then the question is, can we get even more quantitative than that and more local? And so what we started doing is comparing with drop size experimental results and drop velocity experimental results. But that in itself is an incredible challenge, because it turns out experimentally it is not easy to capture equally small drops and large deformed drops. You kind of have to choose what makes it through and what doesn't make it through. So we end up having experimental results that, or let's say the stuff that we compare might not exactly correspond to what's measured experimentally. So on the left here, every time you have the simulation result, and on the right you have the experimental result. This is a plane taken in the back of this jet and crossflow. So we're looking at the shape of the spray cloud as it turns into this plane. So the jet is, the liquid is injected like this, breaks up, and we're looking at drop sizes. This is what we call the Soto mean diameter I think it's in microns. So I would argue that we have more or less the right distribution in terms of the size of the spray cloud. In terms of the sizes of the drops, we're not necessarily quite there, but again, our large drops, we have much larger drops at the top here. We know that experimentally they cannot be captured by the systems that the guys at Georgia Tech were using. So it's ongoing work at this point. We're trying to figure out how to properly compare those results. I'll end with what I consider to be more of a fun exercise, looking at electrohydrodynamic atomization. Could we use a very strong electrode or a strong electric field to help us atomize liquids and more efficiently break up fuel into a spray? So there's experiments out there that suggest that at low speeds you can have a liquid to which nothing happens. And if you put an electrode in the nozzle and form a very strong electric field that leads to the introduction of electric charges in the liquid, you have very intense breakup. So we know that this is a way that we can improve breakup. So this is a model for that. There's really no need to go into details. We have the same Navier-Stokes equations. We just have an additional stress tensor, the so-called Maxwellian stress tensor that essentially gives us the Coulomb force, electrorestrictive forces, etc., etc. We have a Poisson equation for the electric potential. And the interesting thing is that the charges in the liquid can drift. The electric charges will move towards the surface of the liquid-gas interface. But this is an equation, so we can write the transport equation for the liquid charges, but this equation makes only sense in the liquid. There's nothing going on in the gas. There's no charges in the gas. So that's one of those completely discontinuous equations. We have this evolving atomizing liquid, and we need to solve an equation on this. Those are some experimental parameters. I'll just show you a quick movie of that, and then I'll show you the electric field. The electric field. No, sorry, the electric charge field. So the uncharged case, like in the experiment, nothing's happening. We have some turbulence at the inflow, so we see some fluctuations on the interface, but we don't see breakup. The Reynolds and Weber numbers are such that we don't expect to see breakup here. But if we introduce charges, essentially through the effect of the Coulomb force, the self-repulsion leads to this jet breaking apart into a spray. But that's the exciting thing. Using the methodology that we've talked about, we can, on this fixed mesh, everything here is stationary, we can solve for a transport equation of the electric charge that is perfectly conservative and will follow perfectly consistently the displacement of the liquid. So that's not a cut of the 3D simulation, that's a auxiliary 2D simulation, much cheaper to do. But you can see that, yes, we're forming electric boundary layers. We accumulate charge at the surface of the interface. And I'll just finish up with a very limited comparison. We don't have for those conditions an experiment, a detailed visualization of the uncharged case, but it's reasonably easy to find uncharged liquids at reasonable Reynolds numbers. Still, the Reynolds number on this X-ray experiment is, I think, about 3 times larger than on the right. So it's not surprising that the scale of the corrugations is not the same. But that's a typical turbulent uncharged jet. So we think that we're not unreasonable here. For the charge case, we do have experimental pictures, and we can compare side by side on the same scale as simulation with the experiment. If we zoom in a little bit, I would argue that we have some of the same phenomenology, but again, there's a lot of work that needs to be done in order to verify this in more details. All right, I'll stop here. I'll just leave you with these conclusions. We have discussed about second-order, fully conservative, consistent methodology for complex turbulent liquid gas flows. The idea is to deal explicitly with discontinuities, at least to second-order accuracy, and discretize our equations in a way that allows us to deal with one side or the other, both sides of the interface. We've applied that to a number of different flows, and looking forward, as more and more experimental data becomes available, we want to do more and more validation. I didn't talk much about polarization, but the cost of dealing with the interface is much higher than the cost of dealing with cells away from the interface. So we have a domain decomposition paradigm in our code right now, but we're also in the process of implementing, at the same time, a task parallelization idea, so that the most expensive parts of the code can start doing master-slave type work decomposition, so that we don't have the very heavy workloads be concentrated on just a few processes. So that's one of the fun things we're doing right now. And the other question is, I was talking about this volume of fluid as being zeroth order moment. Well, it's very easy to write a transport equation that's completely consistent for the first order moment, the liquid barycenter. It's very easy to write an equation for the moments of inertia of the liquid distribution. All this we can do easily. What we don't know how to do at this point is how to use this information to estimate the liquid distribution within the cell. And we need to figure out a way of doing that in order to make use of those higher order moments. All right, thank you very much for your attention. I'll take any questions.
So I guess that when you incorporate electrostatic forces, they act like body forces, and then I was wondering, how do you deal with surface tension when you generate these problems?
So yeah, I didn't talk much about it. It showed up as a pressure jump. So it's embedded in the discretization of the pressure Poisson equation that we have, that we use in order to guarantee the fact that the velocity field should be solenoidal. So we have a discontinuous pressure, and the surface tension force appears in the discontinuity of the pressure field. It's an entire other topic that we could talk about. The calculation of the curvature itself is also difficult because we have a function that's mostly discontinuous. But there's ways to extract second-order converging curvatures from the volume fraction field. But same thing, I didn't talk about it.
Can you amplify, or maybe say a bit more about surface tension as an issue that's...
So there's really two key issues. One is how to get curvature. That's a tricky exercise. It is not a difficult exercise if you have a level set field. You can differentiate it twice and get very, very good approximation of the conversion. What we have here is information of how much liquid we have in each cell. We need to use neighbor information in order to figure out how the field curves. It's problematic to differentiate across a normal direction of our field since it is a discontinuous field. Differentiating in the tangential direction, however, is fine because it's continuous in the tangential direction. So if you know a priori to a good extent what is the normal orientation of your field, you can pre-integrate your field in its normal direction and transform volume fraction into an idea of liquid height. So you can create in 2D an estimate in the local coordinate system of what is liquid height. And then you can differentiate that twice and figure out to second order accuracy what is a curvature. So that's kind of a tricky thing, but it's something that's been figured out a few years ago, and we're actually working quite a bit trying to figure out how to do that efficiently. Then the issue is how do you use this in order to create a surface tension force. We want this to be sharp, and we want this to be an absolutely local process, and we want this to be also a balanced process. We want to be able to put a drop that's spherical, therefore under tension, and not see it wiggle around and start moving just due to the imbalance of surface tension. So there's a couple of different things that show up here. What we use is the so-called ghost fluid method. So it's a method that essentially relies on embedding the discontinuity of pressure in our discretization of the pressure Poisson equation. So we write discretized operators with the knowledge that if we cross the interface, then the value on the other side should be the value that we have on our mesh, on our grid cell, shifted by the local surface tension times the curvature. And so we write all our discretization is based on those embedded representation of the pressure drop. And that allows us to get, formally at the interface, we're only going to be first order accurate. Globally, we end up recovering second order accuracy, but that allows us to get a local discontinuity of pressure that is also exactly balanced by the pressure force. And ultimately, we're capable of putting a sphere under tension in a domain and not see it wiggle by more than, let's say, the velocity on the order of 10 to the minus 7 or 8, normalized velocity by the order of 10 to the minus 7 or 8.
I've got a less field question. So I've got to do your hierarchy. Let's do 3 points. One is, how does the smallest field of droplet size compare to your smallest viscous field of overflow or turbulence? Or one, of what you see in your droplets. You mentioned at some point there's some very fine scale stuff that you might be captured by just by 2 cells. On one hand, it's not that physically interesting, but it seems that you don't really trust it, but you don't worry because there's not a lot of physical actions happening there. What do you have some skills for mapping models and graphs and stuff like that? Part of the issue, remember, is what's the middle of the little engineers? You folks are doing lab scale stuff, and you're not really pushing the frontier, right, of the computational resources. The surface wave people might really learn from this stuff, but then, you know, you're fighting with, like, a Reynolds number issue in that case, too.
Right, okay, so
hopefully it wasn't too much.
I think it was. So let's go back to question 1
Small
was,
scale of the droplet, how does it compare to the global droplet?
so it depends a lot on the problem. Typically, it will be close. There's an inherent, the fact of the matter is that the ratio of inertia to surface tension and inertia to viscous forces is, you're not completely free to choose those independently. It depends mostly on the velocity of the system. So they tend to be related to one another. We end up very often seeing drop sizes that get close to the. The issue is that we also have, if you start thinking about sheets, breaking sheets, you can have very, very tiny drops. Or if you start breaking ligaments, you can have satellite drops that can be much smaller than tomorrow. So it can be very problematic to be sure what it is we're doing in terms of being absolutely predictive at this point. I mean, when we do tests, for example, we throw drops at each other and we hit pools with drops, compare with experiments, and find that yes, we're capable, provided we have about 10 points in the phenomenon we're trying to represent. We find that we systematically, well, I should say, we almost always get the right number of satellites, the right satellite size, so we verify all those things. But, so I should say we validate all those things, but still there's some level of uncertainty.
Kind of answered the second question. I would assume there's still some population of your droplets, which it sort of acts as a buffer, really. Those length scales, we might have to be sacrificing a little bit, even though it's at a bulk level, the old validation tests.
Yeah, so the questions of the very large scales, or large range of scales, and what do we do at the smaller scales is a big one. There is inherently an assumption that the mesh does the breakup for us, which, if we have a ligament that's being stretched out, it will break once we fall below mesh resolution. But this is also very interesting because it's strongly tied to the numerics. It is like this because we're right now only solving for the liquid volume fraction. And because we have this split reconstruction that's based on the same plane. It means that if we have a very small amount of liquid, that should show up as a neck with 2 planes coming close within a cell. We can't do that because we're right now assuming that our liquid distribution has to be representable with a single plane. So moving away from the split from the fact that a single plane separates liquid and gas from a cell is kind of the same idea as trying to, it would enable us to do subsystem modeling. We would start to be able to say, all right, I can still track my liquid gas interface at the subcell level. Now I need to model how it breaks, how long it's going to take to break. But right now it's not really something we can do because we don't have the numerics to allow us to do it.
Question, then that's question number 3. If you want to push the Reynolds number, maybe you want to sacrifice maybe small scale, maybe something more sophisticated, scale modeling ideas will help. The other is just a computing power, right?
Yeah, so there's a number of things. There's really 2 key parameters. One is the Reynolds number as classical parameter for turbulence. The other one is the Weber number, the ratio of inertial forces to the surface tension force. If you allow them to vary independently, then it's not clear whether what's going to dominate is the smallest, what's going to be the smallest in the domain will be the drop or Kolmogorov. So you have an entire spectrum of problems. Is turbulence a larger scale problem than breakup, or is the breakup a larger scale process than turbulence? If breakup is happening on a somewhat larger scale and turbulence is at a somewhat smaller scale, then you can rely on the classical LES models. And it turns out a number of flows, I think, would fall in this category. So there are ways forward in terms of modeling, larger dissimulation modeling and things like this. There's some difficult aspects and some completely doable aspects, but it's a big field and there's not many people looking at it. Yep.
All right, so we have some bagels and other refreshments next door. If there are more questions, I'm sure Olivier can handle
I'd be
them.
happy to
All right,
handle
so
that.
thanks everybody.